Hi there, welcome back. This is lecture 2, the Perceptron. So the goal today is to derive the Perceptron learning model, which is perhaps the simplest learning model that you could think of. Okay, so we'll derive it, but don't underestimate it. Even though it's a simple learning model, it's very powerful. And in fact, I'm willing to go so far as to say that you can pretty much solve any problem with the Perceptron. Mathematically, that is definitely true. And even in practice, I would claim that if you are having a very hard time solving a problem with the Perceptron, something is going wrong somewhere else. Okay, so we will develop this very simple but very powerful model, the Perceptron. Okay, and then we will pause, and I will sort of specifically address the type of learning we are talking about in this class, which is called supervised learning, in contrast to other types, other views of learning, both highlighting the similarities and the differences. Okay, so learning is a very broad premise, and it has been invented and reinvented multiple times, and in some cases those multiple times have resulted in separate disciplines. Okay, so machine learning is actually going on all over the place, and so it's a useful exercise to sort of see what's going on and how does it relate to what we're doing. Okay, we'll end with a puzzle, so stay tuned. Before we derive the Perceptron, let me just recap where we were from the last lecture. So we talked about the storyline, what is learning, can we do it, how do we do it, how do we do it well, and then let's step back in our storyline and talk about general principles, and lastly we'll add a few bells and whistles with advanced techniques, and we might mention other paradigms. Okay, so that's the plan. Okay. And we introduced the key players, and specifically in the context of this concrete example of credit approval. So, in the machine learning problem, there's an input X. Think of the applicant who applies for credit, and what are the properties, the attributes that the applicant has listed on the application. So salary, debt, years in residence, etc. We call this the input X. The decision that the bank makes, approve or not, yes or no, we call the output Y, and in this particular case we can encode the output by plus or minus 1. Plus 1 approve credit, minus 1 reject for credit. Okay, and this particular type of output is called classification, and this is what we will mainly focus on, although we will touch on when the output can be more than just plus or minus 1. Maybe it can be, let's say, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 digits, so 10 possible outputs. Could be a credit level, in which case it's a real number. Okay, so the output can take many forms. A very popular form is classification. Okay. Now, important, there is some pattern. There's some true relationship that maps X to Y. We call this the target function F. Okay, and that maps X to Y. F, the target function, is unknown, and we mean unknown. Well, it's not totally unknown, because then we're done. There's nothing to do. So in order to learn F, which is the goal of learning, we're given a data set. And in the case of a bank, the bank has data on customers, and what that means is that they have many applications from which they can extract X for each application, the input. Okay, and we assume that whoever's giving you the data can also extract Y, which is assumed to be F of X. So the data set is x1, y1, x2, y2, and so on up to xn, yn. Okay, where we assume that each y in the data set is obtained by applying f to the corresponding x in the data sets. Okay, now how this data set is obtained for the moment is not our primary concern, but it can, in several applications, be a challenging task, especially once we cover the theory and we see what constraints, what are the requirements of this data set deep. Okay? And usually, when machine learning is failing, it's because whoever gave you the data set failed to obey those constraints that are required by the theory. Okay? So it's important to understand the theory for at least one very simple reason, which is that the theory sets the rules for how you can collect a data set. And if you collect it according to what the theory says you should do, then everything else rolls on. If you don't, trouble. Okay? But for the moment, we're not addressing explicitly how does the person who's giving you the data, in this case the bank, how does the bank arrange it so that they can obtain Y by applying f to x when f is not known. So they have to do it in some indirect way. Now, in the case of a bank, we can easily imagine that what the bank does is it gets the applicants who, and checks whether or not after you lent them some money, they paid it back or defaulted. If they paid it back, f is +1. If they didn't, f is -1. Okay. So the input space, the nature of the decision, and the data set are given. Nothing you can do about it. Those set the parameters of the learning problem. The target function f is also in some sense given. It's fixed, but it is unknown. Okay? And the goal is that we have to sort of learn, we have to reverse engineer the target function f from the data d. Okay, so that's the setup of the machine learning problem, and we summarize that in a flowchart. Okay, in terms of step by step, how can we view the entire machine learning process from start to finish? Okay, so the whole process starts with an unknown target function, f. Okay, this unknown target function. So, for example, it's the ideal credit formula in the credit approval. This ideal target function is used to generate the data set. Okay, so you get x1, y1, x2, y2, and so on, xn, yn, using the target function f. Okay, now, you don't know the target function f, so that's where the trick is. You have to somehow indirectly have access to these y's. Okay. In the case of the credit approval application, these are the historical records of existing credit customers. Okay, they are extracted from the historical records. And the goal is a final hypothesis G which approximates f. And so that's the goal. That's the outcome of learning. And if you can output a G that approximates f, I don't care how you did it. Even if you didn't use data, I would say that you have learned. Okay, but when you do use data, we say that you have learned from data. Okay, so the goal here is that you're going to output a final hypothesis G which approximates f, in which case we say that you have learned. Okay, and you are allowed to use the data to output this G. Okay, now we restricted ourselves to a particular mechanism by which you produce this G. And even though I said restricted ourselves, it's essentially without loss of generality. Okay, so where's the restriction? The restriction is that before you see the data, and this is very important, it looks like a restriction, okay, but in the end it turns out to be without loss of generality. Before you see the data, you must fix a hypothesis set H. Set of hypotheses, a set of candidate formulas for credit approval. Okay, and then you say, oh, that's very hard to do if I'm not allowed to know anything about f, I don't know f, and I haven't seen the data. Well, in that case, it looks like a restriction, but if you feel like it's set H to be every function in the world, okay, and then you will not be faced with any restriction here. Okay, but allowing this possibility that you have fixed a hypothesis set H ahead of time, before looking at the data, will make the theory flow. And because that same theory applies no matter what you fix the H to, you can fix it to all hypotheses if you want, so it's still completely general. So fix a hypothesis H, okay, and now you are restricting yourself to, when you see the data, only be allowed to pick a hypothesis from H. Okay, so the game we are setting up, so the learning setup is that you're not allowed to then, after you look at the data, say, I'd like to change my hypothesis set. I'd like to change my set of candidate formulas. Not allowed. Okay. So bear that in mind when you fix the hypothesis set H. Okay. So fix it to something which you are comfortable with. It could be the whole universe of hypotheses, but whatever it is, fix it to something you're comfortable with. Now you get to see the data, and then your learning algorithm is going to pick a hypothesis from this hypothesis set, okay, and output it as the final hypothesis G, and then we will say that you learn if G is approximately equal to F. Okay. Let me sort of talk about three things here. So, first, how does the learning algorithm pick a hypothesis from the hypothesis set? So at a very high level, there's a whole bunch of hypotheses in the hypothesis set that are available to the algorithm. And now the algorithm gets to see the training examples, and it needs to pick one. So in some sense, we have to define some criteria by which it should pick one of those hypotheses. And let me give you some example criteria. Just pick one of those hypotheses randomly. Doesn't sound like a good idea. Where's the learning there? Just pick the first hypothesis. Also doesn't sound like a good idea. Pick a hypothesis that somehow depends on the data set that you now got to look at. That seems like a reasonable approach, but then that somehow is very confusing. How exactly? Okay. So one of the steps in specifying the learning algorithm is to identify what the criterion is that the learning algorithm is using to pick a hypothesis. Okay. So that's one thing that the learning algorithm has to do. And then and it should always bear in mind that the goal is to output a final hypothesis that approximates F, which is a test that you're going to face that is not going to be coming from the data. It's coming from some random other test example. Okay. The second thing that the learning algorithm has to do is it has to actually go and physically perform that task of picking. So there's a criterion that it's going to use in order to pick, but then it needs to go and implement that criterion and pick the hypothesis that's, let's say, best according to that criterion. So that's an algorithmic issue. So there's both the mathematical / learning issue of what's the criterion that the algorithm should use to pick a hypothesis. And then there's the algorithmic computational issue of, okay, how does the algorithm actually now go and search through this hypothesis set, okay, in order to find the hypothesis that satisfies this criterion. Okay, so there's two separate issues here. What's the right criterion, and how do you go and find it? Okay, and in general, okay, we call the algorithm and the hypothesis set the learning model. And in general, when you specify a learning model, you specify this hypothesis set, you must also specify the criterion, and you must also specify the algorithm, because there's no point just telling me, how you should pick it, what the criterion is by which you should pick a hypothesis without also telling me how exactly I should go ahead and do it, how exactly I should go ahead and implement that algorithm. Okay. And then lastly, the algorithm should only care about whether it outputs a hypothesis that's approximately equal to F. And I cannot overstress the importance of that criteria. And let me give you an example. So Edward Jenner. He's the guy who we consider to be the father of the smallpox vaccine. So now, in this whole COVID time, vaccination and so on and so forth is a hot topic. So let me tell you a little bit about how Edward Jenner and then how Edward Jenner and his actions ultimately led to, a smallpox vaccine and then the eradication of smallpox. It's an interesting story, okay? And it is intimately related with this, when I output a final hypothesis, it must be the case that this final hypothesis approximates F. Okay, not the data. Okay, so here's Edward Jenner's story. So around about Edward Jenner's time, so smallpox was raging, but it was sort of well known that milkmaids, so people who would be milking the cows, were sort of immune to smallpox. Okay, and it was conjectured that this is because somehow it was related to the fact that they had cowpox. So cows also had a version of smallpox, which was called cowpox, and then the milkmaids would sort of get cowpox, but this was not a very virulent form of the disease, and so they were able to fight it, and then in fighting it build antibodies for cowpox, but those antibodies helped them to fight smallpox, and so in the event that if they were getting infected by smallpox, they would have immunity. Okay. Now, that's sort of what we know today, but at that time, all that was known was that, milkmaids were immune to smallpox, and somehow it was conjectured by people even before Jenner that, it might be related to the fact that they're around cowpox. That's the data. So in walks Jenner and looks at this data that milkmaids are immune to cowpox and says, well, I'm gonna have a hypothesis. I'm gonna have a hypothesis that if I inject you with cowpox and you survive, then you become immune to smallpox. So that's equivalent to the hypothesis, G here. That's Edward Jenner's hypothesis, which he has learned from the data. So it's an interesting example of real life learning from data. Okay. And how is he going to, convince people that his hypothesis is true? So here's what Edward Jenner did. Okay, so he went to milkmaids who had cowpox, and you have the pox, and inside the pox is pus. This is kind of a gross story, and he pulled pus out. Okay, and his hypothesis was basically that this pus contains cowpox, and so I'm going to inject pus into you, this cowpox pus into you, and then somehow miraculously you're going to get immune to smallpox. Well, this is a very far-fetched story, and it's an interesting hypothesis, G, and it might explain the data, i.e. why the milkmaids were immune to smallpox, but was it really true? Was it really going to approximate a true immunity to smallpox, i.e. would it give immunity to a random new test point? Okay. So how could he test this? So he needed to test this hypothesis, this final hypothesis of his, and so he needed a poor soul who was willing to subject themselves to this test. So he went to his gardener and he said, you know what, I'm going to inject your son with cowpox, and then I'm going to inject your son with smallpox, and then we're going to see if your son gets sick. Now, put this in context. Everyone around these people are dying from smallpox, and he's proposing to his gardener that he's going to inject the gardener's son with cowpox. Okay, well, the gardener doesn't expect the son to die from cowpox, but then after injecting the son with cowpox and waiting for a couple of weeks or whatever till he recovers and gets immunity, he's then going to inject him with smallpox to test and see if the virus works. Okay, so that's the story of Edward Jenner, and you can imagine he must have had a very faithful gardener who really trusted in Edward Jenner, because the gardener said, yes, sure, go ahead, do it, boom. And lo and behold, the son was immune to smallpox, and blah, blah, blah. Smallpox vaccine gets invented, and smallpox gets eradicated. Okay. That is just, to show you that this criterion that the final hypothesis must approximate F, and we don't care how it looks like on the data, is a very, very crucial final criterion for learning. And even Edward Jenner understood it, that my hypothesis explains what's going on in the data, i.e. what's going on with the milkmaid, but I need to be able to show that my hypothesis will work on a new, untested, not in the data point. So not a milkmaid, some random person, and so on and so forth. Okay, so that's just an interesting story that people will go to extremes to prove that their hypothesis is good, and you have to go to those extremes because it's not sufficient to show me that your hypothesis works on the data. Okay, so let's derive the simple perceptron learning model. Okay, and in deriving this simple perceptron learning model, we're going to, identify a hypothesis set. Okay, and then we're going to have to talk about these two things that I mentioned about a learning algorithm. You have to tell me what's the criterion by which you're going to pick a hypothesis from your hypothesis set, and then how are you actually going to do it? Okay, because you need both of those to come through for the learning model to work, to be applicable to a data set. And then at the end of the day, that just makes the learning model applicable to a data set. But is the learning model going to perform learning will come later when you test the final hypothesis and see, does it approximate F? Okay. And we have to talk about how do you do that when you don't have access to F. Okay, so as with all derivations, I find that when you're doing derivations with math and this and that and so on, it always helps to be on a board. Okay, so let's derive this very simple and powerful learning model, which is actually called the perceptron. Okay. And to do so, we're going to use the credit application as a guide. Okay, so imagine an applicant comes along. So we have an applicant. And what is an applicant? An applicant is X, which is salary, debt, years in residence, I don't know, you could ask an applicant for hair color if you want, I don't know, I don't care, etc. Okay, so an applicant comes as a vector of attributes, a vector of features, and remember, we can represent this applicant using its features, which is a input vector x, which is in a d-dimensional space. So let's call this x1, x2, x3, x4, x5, and so on. Now, put yourself in the position of the bank and imagine, they have Malik who's sitting in a dark room, waiting for a task, and the bank says, figure out a way to approve credit. So let's figure out let's try to design a simple, reasonable way to decide whether or not to approve this applicant. Okay? And the basic idea, and it's what used to be used, is, you come up with a score. You could call it a credit score if you want. Come up with a score for this applicant. Okay, so here's the basic idea. Come up with a score. Okay, and if the score is above a threshold, say yes. So in other words, you've come up with a score, and the higher the score, the better. So if the score is above a threshold, some threshold which you also need to come up with, you'll say yes. And if it's below that threshold, you say no. Okay? It's a very simple approach to approving credit. Okay? So now Malik is sitting in the dark room. How might Malik approach the task of coming up with a score? We also have to come up with a threshold. Okay, but let's see how we would approach the task of coming up with a score. Well, Malik can say, applicant has attributes / features. So, these features have different importances. Okay, so let me give an importance level to each feature. Okay, now salary is very important, so I'm going to give it an importance weight of 10. Okay, this weight is 10. Okay, and years in residence is pretty important, so it's going to get a weight of 1. And hair color has absolutely no importance, so I'm going to give that a weight of 0. Okay, and now what about debt? Debt is an interesting guy. Okay, debt is an important factor in deciding whether or not to approve credit. But the higher your debt, the less likely it is that you should get credit. And this score is such that the higher the score, the more likely you should get credit. Okay, so with debt being very important, but being sort of inversely related to score, that means that the weight of debt should be large, but its sign should be negative. It should make a negative contribution. Okay, but that's perfectly fine. I can pick a weight for debt, which is, let's say, -5. So that means it's pretty important, more important than but it has a negative effect. The higher the debt, the lower the score. Okay. So I've given a level of importance to each feature, and the reasonable thing to do, the sort of first thing I might do if I were in charge of approving credit, is to say, let's weight each feature. Let's weight the features by the corresponding weights and add. That naturally produces a number, which I can take as a score. Okay. So weight the features and add. Okay, so I'm going to get 10x1 minus 5x2 plus x3, and the hair color is x4, so plus 0 times x4, so x4, plus and so on. Okay. Now let me put this in a generic form. So this is my score. Okay. So let me put this in a generic form by not committing immediately to the weights 10, minus 5, 1, and 0, although those are the ones that I picked. Let me call this weight W1, W2, W3, W4. So it happens that this is large and negative, small, 0, and so on. Okay, so if we have D features, then we're going to have D weights, okay, a weight for each feature. Okay, and this score, when I put it in this general form, becomes score equals W1 x1 plus W2 x2 plus WD xd. Okay, and now I can implement my rule. Okay, if the score is above a threshold, you say yes. If the score is below a threshold, if that same threshold, you say no. I mean, in theory, you could say I have a upper threshold. If it's above that upper threshold, I say yes. And you could, in theory, have a lower threshold, and if it's below the lower threshold, I would say no. But then what do you do in between? So if you're a credit approver, you have to say yes or no. In between, you might say, well, I'm uncertain, but you're not allowed to be, okay? So we're in this world where you have to say yes or no. Okay? So here's my score, and if this is above a threshold, then you say yes. And if it's below a threshold, then you say no. Very simple approach to approving credit. Okay, and this is more or less how it used to be done. You come up with a credit score, okay, and you compare it to a threshold. Okay, and you know, it's a very natural approach to assigning credit. Okay. So now what I'm going to do is I'm going to take this approach to assigning credit and put it into a mathematically much more convenient form. It turns out that this is a very, you know, it's a formula that I can put in a much more compact, convenient form. So, first of all, the score, okay, is a sum. So, approve, yes, if the sum from I equals 1 to D of Wi xi is greater than threshold. I know if the sum from I equals 1 to D Wi xi is less than the threshold. You might ask, what do you do if the sum is 0? Well, we'll forget about that, you know, very unlikely case. Okay, so we'll brush that under the rug. We can take it into account. We could say, for example, greater equal to, but the mathematics becomes a little bit easier by just ignoring that 0 probability case, essentially, when, you know, the x values are real numbers. Okay, now remember I said that we can encode the yes as +1. So this is my decision is yes, but that's equivalent to saying my decision is +1, and my decision is no is equivalent to saying my decision is -1. Okay. And now we observe that basically what we're doing is we're comparing this to a threshold and saying +1 if it's greater, -1 if it's less. So I can combine these two into an equivalent single formula as follows. Okay. I can take the sign of this value minus that value. Okay. The sum from I equals 1 to D Wi xi minus threshold. And that simple formula is my decision. So let's see if it works. If this sum is bigger than the threshold, then inside here is positive, and so the sign of that is +1, and boom, that's my decision. If this is less than the threshold, this is negative, and the sign is -1. And the fact that I'm not considering the 0 case, so the equals here just means I don't need to define the value of sign when its argument is 0. We could say that it's +1. Okay. Let me further simplify. Let me further address the form of this function by introducing another way W0, which is going to be related to the threshold. So observe that I can write this. Okay. So introduce W0 to represent threshold. Okay. In the sense that if I tell you the threshold, it's equivalent to telling you W0, and I want to write this formula as the sign of the sum from I equals 0 to D Wi xi. Okay, so notice that here the sum is from I equals 1 to D. Here it's from I equals 0 to D. Okay. Now, the I equals 1 to D part of this is exactly what appears here. So this is, you know, it's equal to the sum, the sign of the sum from I equals 1 to D Wi xi plus, okay, there's the I equals 0 term, plus W0 x0. So this will equal that whenever x0 is always set to 1. Okay, so providing that x0 is 1, and W0 then becomes the negative of the threshold. Okay, so this form and that form are basically the same, providing that x0 is 1, so x0 is 1, and the weight W0 is interpreted as the negative threshold. So whatever I said as the threshold, I take as the negative. I take the negative of that for W0. Okay. So this rule that I have implemented, okay, is compactly represented by this functional form where x0 equals 1. Okay. It's a rule. It's a rule that I came up with in a very natural way by constructing a credit score and then using that credit score against the threshold to decide plus or minus 1. The only thing I've done is mathematically simplify that rule into a single formula. Okay. So, let me erase all this and summarize. So, in a very natural way, I came up with the following credit approval rule. Credit approval rule. Okay. My decision. Okay, so let's call it, because it's my final decision. So let's call and relating to the final hypothesis, we call that G. So let's call this G sub Malik, because it was created by Malik sitting in a dark room in the bank. So G sub Malik, okay, is equal to sine of a sum from I equals 0 to D of Wi xi. That is Malik's rule. Okay. Now, what is it a function of? What is G a function of? It takes as input x. Okay. And what about the w's on this side? Well, I came up with those. Remember, there were the numbers 10, 5, minus 5, 1, 0, and so on and so forth. Okay. So I came up with those numbers. Okay. So the only thing that the applicant provides is the x. Okay. And then I implement Malik's final, beautiful rule for credit approval. Okay. Let me introduce a convenient notation. So we can make this functional form even more convenient by introducing a convenient notation. Namely, remember that the applicant x is equal to a vector of its attributes, x1, x2, up to x sub d. Okay. And now we have this, x sub 0. So x sub 0, we have this x sub 0, which is equal to 1 in this formula. Okay. And we have d plus 1 weights. Okay. So w is equal to w0, w1, w2, up to w sub d. Okay. And these are the weights that I came up with in the darkroom. Okay. And just to remind you, w0 is related to the threshold. w0 is equal to the negative of the threshold. Okay. Well, why don't I just forget about the fact that x0 is equal to 1 and incorporate that into x. So let me add a new component to x, which is x0. Okay. Okay. And the original x, so the original x was in R to the d. Okay. Now I'm taking this original x, which consisted of components 1 to d, and I'm adding x0 in here. So we're going to call this the augmented x. So this is the augmented x. And there's no harm done here. Basically what I'm assuming is that, whenever you collect your features of the applicant, just put in a 0th component at the top, which we're calling x0, and set it to 1. So it's always equal to 1. If it's the augmented x, whereas the original x was in R to the d, the augmented x has a component which is 1. So this is in the space which is 1 cross R to the d. So it's got a 1, and then the rest of it is in R to the d. This is one way of telling you that this augmented x always has a 1 in it. Okay. So from now on, for the rest of this course, unless otherwise specified, and we will, when we come to support vector machines, separate out the x0 component. But, for the moment, let us assume that whenever we talk about an input vector x, we will just assume that the augmented part has been put in. Okay, so it always starts with a 1, and then you put in the features. And why is that nice? That's nice because now the the input vector x and the set of importance vectors w have the same dimension. Okay. So this is now in R to the D. This is also d-dimensional, but it's a special d-dimensional space. It's not the general d-dimensional space. The first component is always 1. Okay. So why is that convenient? Because with this representation of x and w, where the first component is always 1, this sum is exactly the inner product of x and w. Okay. So I can replace this sum with the inner product w transpose x. Okay. So it's just a little bit more convenient. Okay. I don't need to keep writing a sum. It turns out that that convenience also translates into algorithms and so on and so forth. So it's more than just pure convenience. Okay. Now, I want to emphasize that this is Malik's rule for approving credit. Okay. And we came up with it using a very natural process of constructing a credit score and comparing to a threshold. So now, we set up a framework for learning. Okay, so we set up a framework for learning in which you have a target function, f, that produces a data set, dn. Okay, and the final output of the learning process is this g, okay, which is supposed to approximate f. Okay, and we said that whenever you produce a g that approximates f, then you have learned. Okay, so in this situation, we have produced a final hypothesis with Malik picking these weights, 10, -5, 1, and so on. Okay, and then a question arises, does g approximate the true target function? Okay, and the answer is probably not, but this is probably a reasonably good way to approve credit. Okay. Now, it's important to emphasize that g sub Malik is not equal to the target function f. Okay. And I'm going to mention at least 2 ways in which this is the case. Okay. So the first is that, well, Malik chose a set of importance weights to use in constructing the credit score and then comparing to a threshold which corresponds to taking the sign here. Okay. So Malik chose W. Okay. And they may not be the right weights. He made a mistake. Okay. And so may not be correct. Okay, that's not a big deal. Okay, maybe we can change the weights. Okay, but there's a sort of more devilish way in which this can be the wrong credit approval formula, which is that the target function has nothing like this simple credit score based formula. Okay, so f does not have the same form as this nice, simple, compact approach. Okay. And we will find ways to deal with this also later. So basically what that amounts to is you need to choose better features. Okay. Or you need to choose a more complex form. Okay. But for the moment, it's just important to emphasize that, I came up with a formula. It may not be the true target function for these 2 reasons. But we will say that Malik has learned the right credit approval formula as long as it approximates the true target function. So as long as this is true. Now, this is the situation where we did not learn from the data. Malik didn't even use the data in coming up with this formula. But our machine learning setup, says that, you have a hypothesis set. Okay, and there's a learning algorithm. So to complete the setup, you have a learning algorithm. Okay, and it's the learning algorithm that produces the final hypothesis by picking one of your hypothesis set from one function from your hypothesis set, and typically you're going to use the data in order to do so. Okay. Whereas here we just came up with the credit rule. So let me show you that this credit rule can be put within this framework. Okay. And all I need to do is to show you that effectively Malik
was the learning algorithm. And what Malik did was pick a specific final hypothesis from a particular hypothesis set. And what is the hypothesis set that Malik was effectively using? Even though Malik didn't, do it that way, but effectively Malik was using all the hypotheses of this form. So let me define a hypothesis of this form as, h of x is equal to sine of w transpose x. Where now I will differentiate between the hypothesis that Malik formed and all the hypotheses of this form by saying that Malik picked a set of weights w star, because they're special. So I'm going to now emphasize the fact that these weights are special. They're Malik's weights corresponding to the 10, the -5, the 1, 0, etc., etc. But a generic hypothesis of this form could be represented as h of x equals sine of w transpose x. So a generic hypothesis of this form. And what is this? That form. Okay. And now that I've come down to this generic hypothesis of this form, we can consider all the possible weights w, okay, that can be used in here, and that defines a set of hypotheses. So let me define a set of hypotheses, a hypothesis set H, which is the hypothesis of the form h of x, where h of x is equal to the sine of w transpose x, and w is in r to the d. Okay, so you give me any set of weights you want that belong to r to the d, okay, and I can construct the corresponding hypothesis, and if you consider all possible weights that are in r to the d, I enumerate in some sense a set of hypotheses. Okay. Now, effectively, what Malik did was pick one hypothesis from this set. Okay. Which one did Malik pick? Malik picked the one corresponding to the weights w star. So this was Malik, the learning algorithm. Okay. And Malik was actually using this hypothesis set in here, picking one of these weights, okay, producing it as w star, and then saying, here, I've got my final hypothesis, G sub Malik. Okay. Now, in that case, he didn't learn from data. Okay. So, the role of learning in this setup is twofold. Well, the first is to replace Malik in that process. So one, we're going to replace Malik. Okay. So instead of Malik picking a hypothesis, an algorithm will pick the hypothesis. So instead of Malik picking, an algorithm will pick. And two, Malik just came up with those weights and we have to trust Malik. But no, the algorithm will use the data. And that's why it'll be an algorithm that learns from the data to produce a G that's approximately F. Algorithm will use the data. Okay, so now, what have we accomplished? What we have shown is that a perfectly natural way of approving credit based on a credit score, okay, corresponds to the learning framework that we had before, the learning problem setup that we had before, with a very particular hypothesis set, okay, containing functions of this form, okay, and, if we can come up with a smart way to pick one of these hypotheses, okay, then we will produce a G, okay, and that's what Malik did. Okay. And we're going to now figure out how to do that without Malik, but replacing Malik with algorithm plus data. Okay. Now, what does our algorithm have to do? The algorithm has to pick, just like Malik did. Although it didn't appear that Malik was picking a hypothesis, he actually was. Okay? And in order for the algorithm to pick, as we discussed earlier, we need two things. We need a way to pick a criterion on the basis of which we will pick one. So in other words, we need a way of deciding, which hypotheses in here are good and which are bad, and then we'll pick one of those. Okay? And once we have a criterion for picking, okay, we need to actually physically go and pick. Okay? And in order to discuss both of those, I want to point out, okay, that Malik did something very sophisticated. And why? Because look, effectively he picked a hypothesis from this set, okay, which is uncountably infinite. So this is uncountably infinite. Infinite. So it's an uncountably infinite set. This hypothesis set is called the perceptron. And sometimes we will also refer to it as the linear model for classification. Okay, linear because it's linear in all kinds of things. It's linear in W. So this W transpose X is what's called a bilinear form. It's linear in W and it's linear in X. So when we say linear model, typically what we're referring to is the linear in W, but the linear in X is also important. And that's going to become clear when we discuss the geometry of the perceptron. That's what we're going to discuss next. Okay, so in order to figure out a way to choose, so in order to figure out the criterion on which to choose and an actual algorithm that does the choosing, it's going to be helpful to sort of at least discuss a little bit the geometry of functions of this form. Okay, and so let's discuss that now. Okay, the geometry of the perceptron. Geometry of the perceptron. Okay, and it's a good idea to do problem 1.2 in the book. Okay, if you're completely unfamiliar with the geometry of the perceptron. I'm going to discuss the geometry in 2 dimensions because it's hard to draw in more than 2 dimensions. Okay, so let's simplify to the case where the applicant is represented by 2 numbers, not D. Okay. And let's imagine that we collect for an applicant age and the income. Okay. And we're looking at this function sine of W transpose X. So this is the weight vector, this is the input vector. The input vector X, so X is equal to 1, remember it's augmented with 1, age and income. Okay, and corresponding to this W is a W0, W1, W2. Okay, now the nature of this linear function W transpose X is that it defines a line. So if we ask what is the solution to the equation W transpose X equals 0, okay, that's going to be a line. Okay, so this is W transpose X equals 0. Now, in D dimensions, this is called a hyperplane. And when you define a hyperplane, there are 2 things that are relevant in a hyperplane. The first is the sort of the slope or the orientation, and the second is the position. So I can have the same slope and move it up and down, and I get a different position. So the position is related to W0, and the orientation, the slope, is related to W1 and W2. Okay? And typically, so this W1 and W2 define the normal. Okay? And okay, so that's the solution to W transpose X equals 0. And then on one side is going to be positive, and on the other side is going to be negative. So there's a positive side, which I will call the +1 side. Okay, and there's going to be a negative side, which is the -1 side. So this is the equal 0, then this is less than 0, greater than 0. Greater than 0 results in +1 when you take the sign. Less than 0 results in -1 when you take the sign. Okay? So that is the geometry of a perceptron. Okay. Now, I want to sort of consider the criterion on the basis of which we're going to decide which one to pick. Okay, so let's consider a second perceptron. So if I have another one here, okay, age, income, okay, and this might be sign of W prime dotted into X. So I'll use dotted into, because it's inconvenient to write the transpose for W prime. So this is W dotted into X, that's the same as W transpose X. This is W prime dotted into X, that's the same as W prime transpose X. Okay, now because it's a different set of weights, it could have a different orientation and a different position. So let's say this hyperplane is over here. Okay. And for this hyperplane, you've got a different normal, okay, and a different +1 region, and a different -1 region. So this is +1, this is -1. Okay. So, when Malik was sitting down, he had to decide, by choosing an appropriate set of weights. For example, imagine that Malik had to make a choice between these sets of weights W and these sets of weights W prime, i.e. between this classifier of people and this classifier of people, and he chose weights. Okay, so he had to decide, he had to pick one of these. Imagine his choice was only one of these two. Okay, now we've gotten rid of Malik, okay, and we're going to ask an algorithm to decide. Okay, and so let's ask the question, which of these is better? And immediately you should think to yourself, well, how do I know which one is better? Okay, and we don't until we realize that, we do have data. Okay. So let me show you what data looks like. Okay, so data is a bunch of applicants. Okay, so you have a bunch of applicants, and what are applicants? Well, an applicant comes with an age and an income. So an applicant is a point in this space. So imagine I have a bunch of applicants. Okay. Now, on this picture, those are the applicants. On this picture, it's exactly the same set of applicants. So I have a bunch of applicants. Okay. And, we have a bunch of applicants. Okay, so that's what the data has. It contains a bunch of applicants, age and income. Okay, but the data has more. The data tells you for each applicant whether or not they paid off their credit. In other words, whether the correct value of Y is +1 or -1. So now what I'm going to do is I'm going to use blue circles to represent +1, blue corresponding to the +1 blue here, and red X's to represent -1. So imagine that these guys all paid off their credit. Okay, so they're +1s. And imagine that these guys both defaulted on their credit, so they are -1s, represented by a red X. Okay, so this is not a good red X. Let's see if I can get a better red X. Okay, red X. Okay. How does it look like? It's the same applicants. So these guys are red X's. Okay. And correspondingly, we've got the blue circles. Okay. Now, I'm going to ask you again. Which of these hypotheses is better? Pause the video. Okay. 1, 2, 3. Okay. I'm back. So if you pause the video and thought, this is the better, well done. Okay, you're implementing a very natural approach to picking the quote unquote better hypothesis. What you're saying is that, look, this hypothesis said blue for all these points and red for these 2 points. So it disagrees with this guy and this guy. Okay, whereas this guy said red for these 2 points and blue for those points, so it agrees with all the data. So this guy looks good. Okay. This guy looks bad. In particular, there are 2 data points on which it looks bad. Now, we mentioned before that, looks good can be deceiving. So just because it looks good, it looks good on the data. Okay, and it looks bad on the data. Now, just because this looks good on the data, does that mean that G equals F or G approximately equals F? Well, that's an issue we will talk about in depth later. But for the moment, okay, we have a criterion on the basis of which to pick. Okay, so criterion to pick. Pick the hypothesis that looks better. Okay, so in other words, when we talk about looks, we mean how does it, compare with the data? How does it look with respect to the data that you have? And when you have data, it's natural to pick this guy because it agrees with the data. This guy doesn't agree with the data. So that's the criterion. Okay. And now we have to implement the criterion and actually do the picking. And you say, oh, well, so now so remembering that, the geometry of the perceptron is that it produces a hyperplane or a line in 2 dimensions. One side is blue, one side is red. How do we pick the one that looks the best? Oh, just look at the data and pick it. Okay. Well, that's a perfectly valid algorithm if you can look at the data and if it's obvious how to pick it. Okay. But in general, your data set is not going to live in 2 dimensions. It might live in, 1,000,000 dimensions or even 100 dimensions. And we can't visualize and we can't look at the data and pick it. So we need an algorithm that implements this criterion and picks the hypothesis that looks the best. Okay? So pick the hypothesis that looks better. How? Okay. So those are the 2 goals that remain. Okay. So we have a hypothesis set. We have identified a criterion by which we're going to pick, and now we need to identify how to do it. We need to give you a way of doing it. Okay. So let's address the how. How to pick the best looking hypothesis. Okay, so here's the basic idea we're going to try to implement. So, step 1. Pick a random hypothesis. For example, this one. Okay. Pick a random hypothesis. A random hypothesis. Okay. And, I'm going to envision that the first step doesn't work. So we're going to have to somehow update it. We're going to have to change it so that it gets better. Okay, so let's call the hypothesis that you pick at step 1 W of 0. Okay, so W of 0. Of 0, I'm preempting the fact that we're going to have iterations, okay, and we're going to gradually improve this hypothesis. Okay, and that's the basic idea. And so we're currently at iteration 0. Okay, and when you've picked a hypothesis randomly, it's typically going to look something like this. It's not going to work. It's not going to look good. Okay. It's not going to look good. So step 2. Okay. So what do you do if it doesn't look good? What do you do if it does look good? So if by chance you happen to pick the hypothesis, which is the line that's going down here and gets everything correct, you're done. Okay. So we only need to address the situation where the hypothesis you picked does not look good. Step 2. The hypothesis does not look good. Okay? So that's the only situation where you need to worry about step 2. Okay? In which case, there's at least one data point on which the hypothesis does not look good. Okay? In this case, for example, there are 2. There's this red X and this blue 0. Okay? Because the hypothesis is saying blue for this red X, and it's saying red for this blue O. So, pick any data point that does not look good. Okay, so for example, this red X. Okay, because we're in a situation where the hypothesis does not look good. And move the hypothesis in the direction that tries to make this look good. Okay, so move the hypothesis in this direction. Why? Because by moving it in this direction, we're trying to make this guy look good. Okay. Move hypothesis to try to improve that bad point. So, how? And what can go wrong? Okay. So let me just mention what can go wrong. What can go wrong is when we move this guy up in order to improve this, maybe we end up here. Okay, but now look at what has happened. We end up here, so everything above there is now blue, everything below here becomes red. So while we did improve this guy and make this guy classified correctly by that line, we've made the situation worse for this guy, and that guy has now become a red, but it's actually a blue 0, a blue O. Okay? So what can go wrong is in improving the situation for one data point, we might mess up other data points. Okay, we'll deal with that later. Okay. Because before we can even address that issue, we need to know how do we move the line up. Okay. So let's consider this situation. Okay. In this situation, okay, my weights, sine of W transpose X. So let's call this X star. So let's call the bad data point, let's call this X star. Okay. So in this case, the sine of W0 dotted into X star has got to be, is positive. Okay, the sign is positive, but the actual Y star, okay, is less than 0, okay, because it's disagreeing. So what we would like to do is we would like to get the sine of W0 dot into X star, we would like to get that to be negative. Okay. So let's look at the situation. So this W dot X star, so W0 dotted into X star is positive because its sign is positive. So what's the situation? The situation is like this. You've got X star and W0. And they're aligned so that their dot product is positive. Okay. What we would like to accomplish is we would like to get W0 to be something like this. Okay. Now they are misaligned and the dot product will be negative. Okay. But how do we get W0 to become something like this? Well, we have to add on to W0 this vector. Okay. But look, this vector is more or less the negative of this vector. So this is negative X star. So it suggests that we should add on to W0 the negative of X star. So W1, so we update W0 to W1, should equal W0 minus X star. Okay? So here we found a bad looking data point, and in order to move the hyperplane, in order to move the line of the hyperplane so that it correctly classifies this data point, we should, in some sense, we should be subtracting X star. Let's look at the other case, okay, which is this blue data point. Supposing we had decided to work with this blue data point, which is also looking bad. In that case, okay, so for this blue data point, for the blue data point, okay, well, the sign of W0 transpose X star must be negative, okay, because this blue data point is on the other side. Sign of W0 dotted into X star is less than 0. Okay. And we'd like to flip it. Okay, so let's look at the picture. So we have X star. Okay, and the dot product is negative. So this is W0. Okay. And we would like to move W so that the two vectors are more aligned, i.e. so that this dot product becomes positive. So we would like W0 to become something like that. Okay. Which means that we need to add to W0 this vector. But look, that vector is basically X star. So we should update W0 to W0 plus X star. So in this situation of a bad data point, W1 should equal W0 plus X star. Okay, so let me summarize. This was the situation when Y star was equal to -1. This was the situation when Y star was equal to +1. And notice that the updates are different. Okay? When Y star is -1, you update by subtracting the data point. When Y star is +1, you update by adding the data point. We can combine both of these into a single update, which is that W of 1 should equal W of 0 plus Y star X star. Because notice, Y star is -1, you have a minus here. Y star is +1, you have a plus here. That's exactly Y star. So minus when it's -1, plus when it's +1. So it's not that this update is any different from these, it's just that it's a compact way of representing this update. Okay. So Hangou is addressed by the update rule. Okay. The update rule. Okay. And now we can be a little more general. So the update rule is that, what we can do is we can say we'll set t equals to 0 in step 1. And the update rule is that you update t, so t equals t plus 1. Okay, so at the first step t equals 0, so now at the second step t equals 1. Okay, and w of t, which would be w of 1, is equal to w of t minus 1, so whatever it was before, plus y star x star, where x star is the applicant data, so it's the input vector for any bad-looking data point. So we make the update. And now we can check. Do you have a good-looking hypothesis? If you have a good-looking hypothesis, you're done. If not, you just repeat. Repeat. Okay. So how to pick the best-looking hypothesis is a very simple algorithm. Well, this algorithm goes by a name. It's called the Perceptron learning algorithm, or the PLA. So, we have simultaneously specified what's the criterion to use in order to pick a hypothesis. We're going to use the hypothesis that looks good, the hypothesis that looks the best. Okay? And what's the algorithm that implements that picking? The perceptron learning algorithm. Okay. So, what can go wrong? What can go wrong? So, 1. Okay. The criterion is bad. In other words, just because it's a good-looking hypothesis, it doesn't necessarily mean that on the next data point that pops up, it's going to work. We'll deal with that question later. Postponed. Two. Okay. The algorithm that does the picking, is considering only one point at a time. So it improves the situation for one point, okay, then it improves the situation for another point, and then it improves and improves and improves and improves. And in improving for one point, it might mess up a whole bunch of other points. Okay, improving for one point might mess up. In fact, it might mess up all the others. Okay. And the third thing that can go wrong is what happens if the data is not separable. So what happens if it is not possible to separate the blue zeros from the red x's? And that's nice. Okay. The red x's. Okay. And this is a serious condition that is not under our control. Okay, so we're saying what happens if it's not possible to separate the blue zeros from the red x's. Okay. So there's no way to construct a hyperplane such that on one side you have all the blue zeros and on the other side you have all the red x's. Okay. Such data is called unseparable data. So what happens in this situation? So let's see what actually happens for the algorithm. The algorithm says, is your hypothesis looking good? If it's yes, you're done. If it's no, you do an update. Okay. Now, for the new hypothesis, can it possibly be looking good? No, because the data is not separable. So it comes back, does the update. Okay. Is the new hypothesis looking good? No, so it comes back, does the update. This algorithm will never terminate. Infinite loop. Now, we have to deal with this for two reasons. One, we don't like creating algorithms that have infinite loops. And two, it's often the case, in fact, it's almost the norm that data will not be separable. Okay. And it turns out that we'll deal with this later. There are many simple tricks that we can use to deal with this situation. One of them is called the pocket algorithm, which we will talk about later. Okay. So, postponed. And so let me just show you that we can deal with the situation where you improve for one point. It's possible that you might mess up all the other points. Okay, so let's consider the situation of separable data. So separable data. Okay, so we're postponing the unseparable data. We're postponing whether or not the criterion is bad or good. Okay, we're considering separable data and asking whether when you improve for one point, you can mess up all the other points. And so here's the miracle of the day. And it's a theorem. If the data is separable, then PLA finds a separator in finite time. So first of all, why do I say finds a separator? Because let's look at separable data. Okay, so separable data, you've got blue circles and you've got red x's. Okay, and you can separate. Okay, so you can find a line that separates blue from red, but if you can find one, you can find many. Okay. And so all we can expect of the algorithm is to find one of them. Okay, fine. Now, why is this a miracle? Okay. Why this is a miracle is because up to now, probably in your computer science career or what have you, you develop algorithms like, here's a list of numbers, there are 4 million numbers, find me the minimum. Okay, so the important thing is, here's a list of numbers, and it has size 4 million, and you can find the minimum. So it's a finite list. Okay, so all algorithms typically operate on a finite object, okay, like a finite list. And then, even if you're struggling to figure out what's the best way to solve the problem, there's always a brute force way. Okay, and what's the brute force way? For example, in a list, you try every element and see if it's the minimum. Try every element. Okay. So we could perform the same kind of algorithm for the perceptron hypothesis set. We could try every possible hypothesis and see, is it a good-looking hypothesis? And that's going to fail miserably because the hypothesis set is infinite. Okay. So this perceptron learning algorithm must be doing something much more spectacular than trying every hypothesis. Okay. And that's what this theorem says, that as long as the data is separable, it's not going to bounce around forever. It's not going to bounce around forever. And so we have managed to find an algorithm that can find a unique guy that separates a very special hypothesis that separates blue from red from among infinitely many. Okay. That's a miracle that it can do that. So let me show you, an example of this theorem in action. So here's an example data set that I've constructed. It's very similar to the one we had on the board. Okay, so you have a bunch of customers with age and income who defaulted, and a bunch of in red X's, and you have a bunch of customers who did not default in blue circles. Okay, and the algorithm starts with a random linear with a random linear separator. Let's even say it starts with 0 weights. So that separator which has 0 weights assigns a credit score of 0 to everyone. So such a credit score of 0 to everyone is going to get all the positive guys wrong. So let's pick one of the positive guys as my bad looking data point and move the hyperplane in that direction, and look what happens. It moves it so much to get this blue guy correct that it classifies everything as blue. Okay, so now there's a bad data point, the red X. Okay, so let's pick this red X and implement the algorithm which moves the weights according to the formula. W is updated to what it was, W before plus Y times X. Okay, so it now moves up, the linear separator moves up and certainly gets the red one we were focusing on correct, but now it's messed up this blue one, and also it still hasn't gotten these other red ones. So let's pick a bad looking data point, this red X in the blue region. Okay, update. Oh, now it's classifying everything as red. And so this is exactly what we talked about, which was the problem, that in trying to get one data point, so before at least 4 of the blues were looking good, but now in trying to get this red guy to look good, boom, we messed up all the blue guys. And the worry is that will this go on forever? So if we continue, it's almost correct and almost messes up and more, and boom, now it's finally done. Okay. And that's the theorem at work. It says that you can keep bouncing around like this, but only a finite number of times. Eventually, you will find a separator. And the question then becomes, after how long? Well, you will answer that to some extent in the homework when you prove this theorem. And of course, we already mentioned what to do if the data is not separable. And here's an example of data that cannot be separated by a line. Okay. So, bottom line, which we already mentioned, is that from the computational perspective, we can search this infinite set. That's a miracle that we can search an infinite set. Okay. And we can find the hypothesis that looks good. Okay. But then, the question is that just because it looks good on the data doesn't mean that it is good. In other words, remember, we want to predict on a new data point. And we will discuss that issue at length. Trust me, we will discuss that issue at length. Okay, and one of the things that crops up in discussing that issue is whether it's even possible for a limited data set like this to provide information that will allow me to predict outside the data. Okay, and we will discuss that issue at length. Don't worry. Okay. So let's briefly digress towards other views of learning, and then I'll show you a puzzle, and then we will discuss that puzzle later. So other views of learning. So remember, learning is a very broad premise, and it's cropped up and even
created other disciplines. Okay, so let's first distinguish learning from design. Okay, so learning is occurring from data. Design occurs from specs and a model. So let's say I wanted to design, a vending machine that, recognizes dimes and quarters. So what do? I call up the US Mint. I get, the specifications by which, the quarters are made and the dimes are made, and then I can build a formula that says, if the radius is above this value, then it's a quarter. Okay, so that's if you give me perfect specs for a problem, I can design a solution. That's kind of like the situation where I know the pattern. Okay, so learning comes in when you don't know the pattern. Remember, that was one of the fundamental requirements for learning to be relevant to solving a problem. Okay, now there are these fields like statistics, okay, which are mathematical. Statistics and function approximation, which are sort of very mathematical disciplines, where the goal is to derive rigorous answers to certain questions like, can I identify a probability distribution, or can I identify a linear regression, and what theorems can be proved. So in those settings, we typically make many strong assumptions and then prove a theorem like, if this, then we can identify the probability distribution. So it's a brand of learning because you use data to learn something, but it's sort of limited in scope because of the nature of the types of results you try to get, which are very rigorous results. Here we're going to take the opposite approach in some sense. We're going to assume that the type of function that you're trying to learn, we don't know anything about it. It is completely arbitrary. Okay? And then you get some data that represents that function, no matter what it is, and then we're going to give it a go with learning, and then we're going to see what happens and what can we conclude from what happens. There's a field called data mining that's focusing a lot on the sort of notion of finding patterns in massive data. It's very closely related to learning, and in fact, some learning courses masquerade as data mining courses, some data mining courses masquerade as learning courses, so those are very closely related. But from the perspective that we are going to present, data mining courses tend to be more algorithmic in flavor, more about, can we find all the patterns efficiently. Typically, data mining is unsupervised, but nowadays, data mining and machine learning are sort of sometimes used interchangeably. When it comes to learning, there are three main paradigms, okay? And the three main paradigms are supervised, which is the context of this course, okay? So where the data is, remember, xn and y, so you get an x and a y in the data, okay? So you are told the answer. So for my applicants in my data set with respect to credit approval, I am told that for this applicant, the correct answer should have been to approve. So I'm told f of x. Okay. Now, the other three paradigms are basically versions of the supervised paradigm where you change the data. Okay. So in the unsupervised paradigm, you don't give me f at all. Okay. So you just give me all the applicants. You say, here's a bunch of applicants. Okay. And the idea here is that you can learn to organize the data so that when later you give me a few values of f on a few data points, it might be very easy to then build a predictor. And a lot can be gained by an efficient and good way to organize the data. Okay. Reinforcement learning is a very common type of learning and it's a very intuitive type of learning because that's mostly the way we learn. Okay, so instead of giving you the right answer, I let you try something. So you're a child, you see a hot cup of coffee. I let you try to touch that hot cup of coffee. Okay, I let you try. You try to touch the hot cup, you get burned. Okay, you try to touch the hot cup of coffee, you get burned. Now, I'm not telling you don't touch the hot cup of coffee. I'm just presenting you with a situation. You try and get burned. You get burned. You get burned. Eventually, you'll learn that if there's a cup, that's placed on the table and it's got liquid in it and it looks this shape of a coffee cup, I'm not going to touch it. Okay, and you learn the correct decision, which is don't touch. Okay, but you didn't learn it because someone told you don't touch. You learned it because you tried and repeatedly got burned, and so you then inferred that, oh, maybe it's better not to touch. But you'll never know for sure, okay? Because every time you don't touch, you are also probably feeling some pain. What's in that cup? What's in that cup? I want to touch. Okay, but so you never really know what's the right thing to have done because you'll have many episodes of curiosity not being fulfilled. Okay, but you have to compromise between the amount of times you touched and got burned and the amount of times you didn't touch and your curiosity was not satisfied. Okay, so in reinforcement learning, you see an input, the cup of coffee or the cup containing liquid. You try something and you get feedback, and somehow miraculously you learn not to touch the cup of coffee. In fact, reinforcement learning is quite a powerful method of learning. It is this method that was used to create some time ago, create the world's best machine learning backgammon player. Okay. Let me show you a little bit about unsupervised learning, just to show you that organizing the data is a very powerful pre-processing step that can aid a lot in the learning process. Okay, so here is an example of a learning problem, just like the credit card approval, where instead of age and income, we look at size and mass of a coin. And if you plot the size and mass of a coin for dimes, pennies, nickels, and quarters, it'll look something like this, where the colors indicate, the denomination. And then if you are asked to separate these with a linear model, you might do something like what's on the right here. So anything below this first line is a dime, then between the first and second line is a penny, and so on and so forth. Okay, so you have learned from the data. Okay. Now, in the unsupervised setting, I'm going to give you this data, but I'm only going to give you the size and the mass. I'm not going to tell you that these are dimes and these are pennies. I'm not even going to tell you that there are 4 types of objects. I'm just going to give you a bunch of objects, okay, and they're going to have different sizes and masses. So let's look at what that looks like. Wow, there you go. Okay, so that's the same data, but now I've removed the color because I've removed the label, the f of x. So x is size and mass, and f of x is the value of the coin, and I've removed the value which was encoded in the colors. Well, when you look at this, you'll see that while yes, there's significantly less information, when you look at this, at least as a human, intuitively you can identify some structure, okay, which you can try to organize into 4 types of objects. Okay, so here, when we have this unsupervised setting, we might still construct the same lines. Okay, so there's a lot of information here. I just don't know that what's below the first line is a dime. I just know that it looks like there's one type of object here, another type of object here, a third type, and a fourth type. It's also possible that you will say that there are only 3 types of objects. This big group here, and then this and that. And that's one of the challenges with organizing data, with organizing anything. So if someone comes to you and says, okay, my mom came to me when I was like 12 and said, Malik, you need to organize your books on your bookshelf. I'm looking at it and what the hell does that mean? Okay, but now just organize them. Put at least the books of one topic on one side and then the next topic and so on and so forth. So I'm thinking to myself, okay, that makes sense. Let me organize my books. Okay, so I'm trying to organize. I'm trying to figure out how many topics. Okay, that corresponds to how many groups here would be appropriate for organizing this data on size and mass. And if you happen to decide to organize into 4, then you might almost learn as much as in the supervised setting. Now if someone comes and says, you know what, this type 1 that you organized into, well, those are actually called dimes, I'm ready to go. Anything that comes in here I classify as type 1, and you told me it's a dime, so it's a dime. Okay, so that's unsupervised learning. And that constitutes the end of this lecture, except that I want to give you a puzzle. Now, in this puzzle, I'm going to try to put you into the frame of mind of a computer, of a machine learner. Okay. Now, it's going to be a visual puzzle, so if I ask you to tell me in a picture whether or not there's a tree, you will have no problem. And that's because you have a huge experience. Okay. So, contrast that with a machine learning algorithm or a computer which is going to be faced with data and has to learn what a tree is. Well, they're starting from 0. Okay. And so I'm going to try to put you into that same situation. I'm going to start you at 0. And this is important. Okay, so I'm going to show you some pictures of trees and dogs. So that's your data. And I could play the same game with a computer. I could show the computer some pictures of trees and dogs. Okay. And I'm going to show you those same pictures. Okay. And then I'm going to show you another picture, and I'm going to ask you whether that picture that I'm showing you, you can think of it as a test picture. I'm going to ask you, is that test picture a tree or a dog? Okay, so here we go. So on the top row, I'm showing you some pictures of dogs. On the bottom row, I'm showing you some pictures of trees. Okay, now you're supposed to halt me and say, wait, whoa, 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 Malik, those things are not anything like dogs. Okay? And these things at the bottom are nothing like trees, but that's the point. They're nothing like the dogs you know, and they're nothing like the trees you know, but I've put you on a brand new planet where you have no experience. Okay? And this is my way of doing that. This is my way of wiping out all your experience. I'm showing you the data and you have nothing else other than the data to help you. So this is to give you a real feel for what is learning from data. When you're learning from data, the data is the only thing you have about the target function f. Okay. And the fact that you're telling me those are not dogs and those are not trees is your attempt to use the information that you already have, your extensive 25 years of experience or whatever it might be. Okay. And I'm wiping that clean. Okay. I'm saying, no, whatever planet you live on, I don't care. You have now come to Mars, and these are what dogs look like. And these are what trees look like. Well, as in, here are 3 examples of dogs, here are 3 examples of trees. Now please tell me, is this thing a tree or a dog? Okay, so pause the video and write it down. Okay, so if you pause the video and wrote it down, well, you know, you're not allowed to change it, but keep in mind what you said as I'm about to discuss what happens when I ask this to an audience of about 200 students in my machine learning class. And I did this the last time I taught it live, and I do it every time I teach the course live. Unfortunately, in this online environment, it's not easy for me to tally the results. Okay, but when I do this with my students in the class of about, let's say, 200 students, okay, approximately 60% of them say that this guy is a dog. And approximately 40% of them say that this guy is a tree. Okay. And we can go and try to analyze what's causing this 60% to say that this is a dog, and what's causing the 40% to say that this is a tree. And when I talk to people and I try to perform any kinds of correlations and so on and so forth, it turns out that the people who say that this is a dog tend to be computer scientists and or engineers. Okay, the people who say that this is a tree tend to be, you know, sometimes physicists, you know, coming from management, coming from biology. Okay, and you know, so and what's the reason they give me for this being a dog? The reason they give me for this being a dog is they say, well, look at the top left pixel. Okay, so black, black, black for all the dogs, white, white, white for all the trees. And this is black, so obviously it's a dog. And computer scientists and engineers tend to look for this kind of an explanation, some kind of a quantitative, you know, look at the top left pixel. I don't know why. I mean, I'm not saying that this is the explanation, but that's sort of something that I've observed. Maybe I'm just conning myself. That this is what computer scientists and engineers tend to do. And then the other people tend to go for something more complicated. Okay, they say this is clearly a tree because look, the trees have some form of symmetry. Okay, and the dogs look like totally random things. Okay, like almost like an amorphous image. So if it's an amorphous image, it's a dog, but if there's some kind of structured pattern / symmetry, then it's a tree. And then you ask, well, what do you mean by symmetry? Oh, I don't know what I mean by symmetry, but you know, so that's using experience in some sense. I don't know what I mean by symmetry, but you know, you know what I mean. It's symmetry. Okay. So I said, well, I don't really know what you mean, but I sort of I'll play along. Okay, and then they claim that, you know, according to whatever intuitive definition of symmetry they are talking about, this thing has symmetry, and so clearly it's a tree. Well, symmetry, it turns out, is a very complicated concept, and they're using a very complicated rule in order to classify tree or dog, as opposed to the computer scientists who are using a very simple rule. So which is right? I'm not going to tell you which is right. I'm not going to tell you is it a tree or a dog. Okay. Because that wasn't the point of this whole exercise, even though I spent some minutes on it. The point of this whole exercise is that 40% of you would say that it's a tree. I don't care why you said it's a tree. Okay? 40% of you said it's a tree. And 60% of you said it's a dog. I don't care why you say it's a dog, but 60% of you say it's a dog. And so I'm going to, you know, summarize in this way. Okay, I gave you some data. In this case, it happens to be 6 pieces of data. Okay, and then I presented with you a test point, which is the scenario of learning. So you can do whatever you want on the data. You can learn from the data and say it's a top left pixel. You can learn from the data and say it's all about symmetry. Whatever you learned, I don't care. Okay, because that's going to be your way of explaining the data. But when I come to a test point, approximately half of you say one thing, and approximately the other half say another thing. Okay, so now why is this interesting? Okay, why this is interesting is that it is sort of a working assumption that the human is the planet's supreme learner. Okay. Now, the purpose of this course is to try and pin down learning so that we can get a machine to learn. Okay, but what's our gold standard? Our gold standard is the human. So we're trying to get machines to learn and be able to do things that humans who learn can do. And if the world's supreme learner cannot agree about what this test point is, then how can we hope to build a machine learning algorithm that does so? That is the puzzle. Okay. And indeed, it is the case. I mean, we cannot fault either of those sets of humans. The set that said it's a tree, well, it could be a tree if symmetry is the right target function. Okay. It could be a dog if top left pixel is the right target function. The point is that it's impossible to break that tie. Okay. Because both could be right from a theoretical perspective. Okay. So we then said, well, let's not appeal to the theoretical perspective. Let's appeal to humans who are the world's best learners. Okay. And let's see what they say. And they don't agree. This is a problem. So from the theoretical perspective, either could be right. And the world's best learners can't break that tie. They don't agree that it's a tree or a dog. So there's something fundamental that we need to pin down. Okay? Otherwise, it looks like learning is not possible. And indeed, we should suspect that how is it possible that a small finite data set like this can tell us how to predict on unseen data. And if the target function f is truly unknown, okay, then its value outside the data can truly be anything. So how does the data help you in any way whatsoever in predicting outside the data? And why do we care about predicting outside the data? Because that was the fundamental definition of what it means to learn. So here we have a puzzle, and we better resolve this puzzle, or else the course is over. Or else we say you cannot learn, you cannot predict outside the data. So, but learning is alive and well, so something is going on and we need to pin it down. Okay, see you next time.